So let's take a beam of length 8 meters and it's carrying a uniformly distributed load of 5 kilonewtons per meter over the entire length. And our goal is to really replace this distributed load with a single equivalent point load. And we want to also state where this equivalent point load will act on the beam and briefly explain why this equivalent load can replace the distributed load. Now, a uniformly distributed load, and I'll start saying UDL from now, of 5 kilonewtons per meter means that every meter of the beam, it's carrying 5 kilonewtons of force. So instead of one force, we actually have a continuous spread of one force acting along the entire beam. And that force is 5 kilonewtons per meter over 8 meters long. So that's what we have dealing with here. Now, to replace this distributed load, we first need to find the total force acting on the beam. So we do that by multiplying the load intensity by the length. So we have the total load equals W, which represents our UDL or omega times the length of the beam. So this would give us then our 5 and multiplied by the length of the beam of 8. And you will notice the difference as well, where this as a unit is now 40, but the unit is kilonewton. So this is now converted to a force. And I'll show you what happens with the unit just so you're clear with that as well. So this 5 is kilonewtons per meter, and it's been multiplied by a unit of meter or 8 meters. So when we cancel them meters out, we're just left with kilonewtons. Now, what I would typically recommend here is that you redraw the beam if you have any difficulties seeing exactly how this works. So you would just sketch that beam. So that's the sketch of the beam. Put the supports in. And what we're going to do now is to use this 40 kilonewtons as a point load. Now, for a uniformly distributed load, the equivalent point load, it always acts at the center of the load. So what we'll have now is here a point load right there of 40 kilonewtons. And if the full length of our beam is 8 meters, then that point load would be acting at the center. So on either side, we would have 4 meters long and 4 meters long on either side. And this works because the equivalent point load produces the same overall effect as the distributed load. So in particular, it creates the same moment about any point on the beam. So even though we've simplified the load into a single force, the physics of the problem remains exactly the same. So the point load here of 40 kilonewtons at 4 meters will have the same effect as this spread of 5 kilonewtons per meter across the 8 meters. So whenever you see a uniformly distributed load, just remember, multiply the load by the length to get the total force and place it at the center. Now in the next video, we'll look at what happens when the load only covers part of the beam, and that's where things get a bit more interesting. So I'll see you in this next video right here.